And here we are back again with some example problems on solving the volumes with given cross-sectional areas using integrals. So we have here on problem number 1 that we are going to find the volume of a solid whose cross-sections are squares that are perpendicular, that good old geometry sign, perpendicular to the x-axis, and the base of the solid is bound between the function f of x is equal to x multiplied all of 2 minus x and the x-axis. Okay, so we've got a few things going on here, one of which would be a lot easier if we were able to see what the function would look like. So as a little bit of a note, something that will be easier to graph is maybe something in the form of 2x minus x squared. Either would do, but in terms of what we're going to do here today, usually starting with a graph, if it hasn't been given to you already on the problem, would be a good way to visualize how we're going to come about solving for that volume that they're asking for. So again, we're dealing with a sort of graph here. In this case, given that it's the 2x minus x squared, we are only really going to be going to the right side direction here. So at 0, 0, we have a point, and at 2, 0, we also have a point, given that it's 2x minus x squared. And then at 1, 1, we have a point. So it's a little bit small, at least for what we have here, but we get an idea that we're going to have some sort of curve like this, given that it's a negative on the parabolic sense there. And so again, it says here that the cross sections are going to be squares. So we can really make sure we can, if we can extrude it, even though it's kind of constrained on the two-dimensional plane, we are making squares that are perpendicular to the x-axis. So again, it's cutting down vertically across the x-axis, and we need to integrate it across. Thankfully, because we know that we're binding it between those 2 points and the x-axis, that just means that our integral will begin going from 0 all the way to positive 2. Okay, that is where our integral will start and finish. But now we have the issue, of course, is that we are dealing with squares, right? Meaning that we take that height of the square and then we just simply multiply it by itself inside of the integral. In this case, because we're only measuring that distance just from the top of the function down to the x-axis, all that really means is that we are taking the overall function, f of x, and then we just raise it to the second power. And in this case, this is a very simple example for us to be able to set up an equation in order to solve for this kind of volume, and then we start multiplying across and then integrating. So if we actually want to substitute that, if we need to go over the actual calculation itself, if they were going to ask for the actual volume itself, which we can very easily calculate this by hand, we will take that same integral going from 0 to 2. Now it's going to be replaced by the 2x minus x squared, all of that squared, by dx. And so we just simply FOIL it out, and then we can work our way into integrating this problem. So that will mean we need to take the FOIL for this, which is going to be all of our 4x to the second power minus a 4x to the third power plus an x to the fourth power. So keeping track of all of our algebraic rules on being able to distribute that squared across the 2x minus x squared will result in something like this. Then from here, we can just go across and simply integrate across each of those terms. So we end up with 4 over 3x to the third minus a simple x to the fourth plus x to the fifth over 5. And we are evaluating the limits from 0 to 2 as before. And so now, in order for us to then fully define our volume that they were asking for, we just need to do our definite integral limit analysis. And so for our first term, we have 4 over 3 multiplied by an 8, because it's 2 to the third power, minus a whole 16, because it's 2 to the fourth power there. And then we need to add a 32 over 5, which is 2 to the fifth power over there. Okay? And so for something like this just simply takes a little bit of additional, I think in the best case is just some algebraic knowledge. But working through this, you'll be able to simplify this all into a nice and easy 16 over 15 if the work checks out which I would encourage my students at this point to just try it for themselves if they need to do any additional practice on doing this kind of simplification. The silly mistakes are definitely going to be a killer for many students, but this will be the most simplest way of writing out this kind of answer once you work your way through the rest of this problem. Okay, so that should just about do it for this problem. Again, I think for this unit, we are mostly going to be focusing about learning how to set up that integral such that you can actually do the integration either by hand or through calculator, or in many cases, as seen through the live streams when we go over many different old AP problems, is that they will ask you just to set up the integral in the definite integral sense and then not even solve it. Your answer would actually end right here after you know how to set up a type of problem like this. And that is exactly what we're going to do going to our next problem right here. Whew. This problem is what I call a real banger. Well, let's read this through first. As you can see, there's a lot going on with that graph, but let's have a look what this problem is asking for. It says here to find the volume of a solid with cross sections perpendicular to the x-axis and are isosceles right triangles with a hypotenuse laying on region R, which is bound by the function f of x, similar to last problem of x multiplied by all of 2 minus x, and the other function g of x now going underneath being equal to cosine of pi x minus 1 on the outside, as shown exactly on that graph. So we've got a lot of things going on here, which we need to take measurement for as we try to solve it. First off, of course, is that we are once again going perpendicular to the x-axis. That's pretty nice. But they are asking for right triangles, again, the ones that are isosceles right triangles, with the hypotenuse laying across region R. So that's a lot of details in which we need to use in order for us to set up this problem. So something to note here is that while we do know that the hypotenuse will be going vertically downwards across those two functions, something that is going to happen on this type of problem is that this is a calculator problem. Okay, although isn't explicitly noted here, is that because of the complexity of this type of problem, this would normally be a calculator problem on the AP exam, or a type of problem which they are just going to ask you to set up and not solve. At least in our case, that is still going to be one of the main points of this video, is to make sure that we can set up the problem correctly and then go about running it through the calculator or leaving it as simply just the integral. So we'll be going through both parts of the setup and showing you what that looks like on the calculator and the appropriate answer to that. But even then, we still need to understand all the details as to what they are even asking for in the first place. So to note here, of course, is that we are dealing with isosceles right triangles. That means that we got ourselves a right triangle with each of the legs that are congruent to each other, except now, instead of one of the legs being on the graph, we have the scenario where we have the actual region R going vertically across the two. So again, our hypotenuse is going to be here f of x minus g of x. And again, something to note is that even though some students might think, well, why are we subtracting g of x? As you can see with the example line that we drew of one of the hypotenuses that this will be, why are we subtracting g? Are we taking away the height? Well, when you think about it, g of x actually has all these points underneath the x-axis. And so if you did subtract f from g, well, then you're subtracting negative values and then you are going to add to the height to it. Again, the principle that I explained in our first video in this series of going the top minus bottom still holds. All right, so that even though we have parts of the function that are going underneath the x-axis, by subtracting it, you are still adding to the total height because you're subtracting negative values on the y's. Okay, so because of that, well, we need to still figure out, well, like, what about the area business, right? We have the hypotenuse, which is great, but of course the actual volume would be set up by taking our definite integral going from a to b, but then of course we need to take an area, all right? And in case dx, of course, because we're going perpendicular to the x-axis, we're going by heights of x, so that's no problem. But still, what about the area? Well, of course, in this case, area is going to be 1/2 the base times height for any sort of triangle. Thankfully for this triangle, the base is literally equal to itself, so it's just going to be 1/2 b squared. Not a problem, but we're still not having what we need. We still need to know the base, one of these legs, while we only have the hypotenuse. So for those who are going through this for the first time, let's quickly go over how to get that relationship from a hypotenuse of an isosceles right triangle into one of the legs, because that is what we need to find the area. So of course, we can go ahead and describe, instead of our case here, again, we'll call it C for the hypotenuse, as before for any sort of right triangle. But instead, let's use L instead for any arbitrary leg that this will be. So of course, we can refer back to Pythagorean theorem as the main way to draw the relationship between the legs of a right triangle and its hypotenuse. And then when you simply put all the like terms together, we get 2L squared is equal to C squared. But then again, we know what C is. We know what the hypotenuse is. We defined it as F minus G, so there's no problem there. But then of course, we need to isolate the leg because we need to know that in order to find the area. Then we will integrate afterwards. So because of that, we can then isolate L by dividing that 2 to the other side. And then one leg itself is going to be equal to, relationally, the square root of C squared over 2, which in our case, by getting rid of that C squared from the square root, that's just going to be a positive C over the square root of 2. That is how you draw the relationship from any hypotenuse of this type of triangle into a distinct leg. So we can actually draw this all the way back exactly where we need to go for this type of problem, in that we have the 1/2 base squared. So again, that's going to be one leg squared as we take the integral this time. Now, again, if you look at where they're intersecting, they'll be intersecting from x of values of 0 all the way to positive 2. So going from 0 to 2 on that integral. But then, of course, is that instead of calling it a leg squared, that's just going to be L squared overall, in which thankfully we already have that step earlier that we can easily substitute for, so that we can leave the 1/2 on the outside, and then we go from 0 to 2 for C squared. In this case, C in this case will be f of x minus g of x, so we can write that down. So all of this can be squared, and we divide it by 2. And so lastly, we can simply go ahead and throw that 1/4 to the outside, and then run the integral from 0 to 2 for all of f of x minus g of x, all of that squared dx. Okay? So for something that we are ready to put into the calculator here, then if we want to set up the entirety using the actual functions themselves, then we end up with 1/4 multiplied by the entire definite integral going from 0 to 2. Now we have f of x already labeled as the x multiplied by 2 minus x, and then subtracted by g of x, which is the cosine of pi times x. Now we are subtracting it with the -1 at the end of there, so we can leave it as a +1, and then with all of this being squared in terms of x. So this will be the setup for the problem, and this will exactly be what you can put directly into the calculator, as we can show you right here off to the side. Again, at least for me, I'm using, as you can see on a lot of the live streams, I'm using a classic TI-83 Plus as something that I grew up with and can still use for this exam. And so with that, if you plug everything in just right, you should be ending up with the actual answer of the 7.544, leaving it at 3 decimal places, as the approximation to that volume with those exact cross sections. Okay? And so with that, that really is just as far as we need to go. Again, if for those who really are looking to run that integral by hand, you can go right ahead. But in terms of the difficulty for the types of problems that they'll ask on the exam, this will not be something that's done by hand. It will usually be done, again, either A, by calculator, or B, like here, leaving it as such as an integral, just in that form as a way of you showing you know how to set up this integral. The calculations will deal with itself at a later time. So because of that, the actual area resulting from this and then integrating to a volume of 7.544 will be the correct response to this problem. So there are a lot of other things we still need to go over as we will be getting into rotations, either through the disk and shell methods, both of which will require their own lectures. So we have our work cut out for us. And again, you can always email in any of your questions at labcoatmath@gmail.com. And we shall be seeing you there next time, as we'll be streaming tomorrow, as well as cooking up a few new series for us to finally start responding to the emails that are coming in. So that will conclude it for today, and we'll be back tomorrow with some more questions and lessons about doing rotational volumes across certain axes.